Cool. So, little intro. Welcome, everyone. I am Mitali. I am Senior Data Scientist at Saturn Cloud. And today I will be talking to you about getting started with Dask using Saturn Cloud. So before deep diving into any of the data science stuff, I want to talk to you about Formula One. So whenever there is a Formula One tournament, there is a pit stop. This pit stop lasts for 2 to 4 seconds. In fact, the shortest pit stop has been of 1.84 seconds. And in this small duration, many things are done. Tires are changed, mechanical adjustments are made, or refueling is done. Now, how is it possible to do so many things in such a small amount of time? It is possible because there are n number of people who are working together. So there is this one big task, which is pit stop, but they have divided this task into small parts. And this is exactly what parallel computing is. It is dividing the problems into small parts and solving at the same time. So now we know what parallel computing is. But why do we need parallel computing in data science? Python is a friendly language. It is used by so many data scientists across the world. It is my favorite language. But Python on its own is not fast enough. So there is this log, which is known as global interpreted log. Today, I won't be going into the details of what this log is, but what happens because of this log is that Python is not able to utilize multi-threading for CPU-intensive computations. And that is why it needs some toolkits like Dask, like Spark or Ray to help distribute the work across multiple cores if you are using a single machine or across multiple machines. And what all can we do with parallel computing? So imagine that you have got lots of data. You have got like millions or billions of lines, and you are trying to load that data on your machine. What if the size of your machine is smaller than the size of the data? You will get out of memory error. Or let's say you are trying to do hyperparameter tuning. I mean, it has happened with me so many times that I start doing hyperparameter tuning, I go out, I come back, and my model is still running. So for all these cases, you can use parallel computing and make your computations run much faster. So of all the toolkits that I have showed you today, I would be talking to you about Dask. So what is Dask? Dask is a free and open source library. It is written in Python, so it's a big advantage if you are a Python user because debugging becomes really easy. Dask will increase the speed of your computations, so you can distribute your work across multiple cores if you are working on a single machine, or you can use something like Dask distributed and work on multiple machines. And the best part is that Dask is easy. So if you know how to do your computations or how to write your functions in Python, then switching to Dask is not a big deal. I will be showing some examples around that. So for all those examples, we will be using a data set, which is a Formula One data set. We have this file, which is known as labtimes.csv. This has been taken from Kaggle. And in this file, we have race ID, we have driver ID, we have lap, position, and time for each lap. So before deep diving into the examples, let me talk to you about Dask networks first. Now, Dask networks is made up of 3 things. It has a client, it has a scheduler, and it has workers. So client can be thought of like a user-facing entry point where you are writing your commands. Scheduler is the one which is actually managing all the workers. So it is getting the commands from the clients and it is assigning these to all the workers. And workers are the ones who are actually executing all these tasks in parallel. They are saving the data in parallel and they are also communicating with each other. And there is this term Dask clusters. You might have heard it maybe somewhere, or you might hear me saying it moving forward. So whenever people are talking about Dask clusters, that means scheduler and workers. So now let's talk about user interfaces of Dask. Dask has got two kinds of user interfaces, a high-level interface and low-level interface. Now, high-level interface can be thought of like a scalable version of NumPy and Pandas. So the standard interface remains same. Saying that means that the syntax you would be using is more or less same. But under the hood, things are different. Dask would be using parallel computing. So your computations will be much faster. And then comes low-level interface. So imagine that you have a custom algorithm. It is written in single node. Let's say that you use Pandas and you wrote n number of functions. And later you realize that, hey, I think I need some scalability. And you don't want each and everything to be changed to something like Dask DataFrames or Dask arrays. What do? In that case, you keep your custom algorithm as it is. You don't make any change to your single node custom algorithm. You just wrap it with something like Dask delayed or Dask futures. So now we would be seeing each of these in detail one by one along with example. So the first one is Dask DataFrames. Dask DataFrames can be thought of like a bunch of Pandas data frame. Just the way here you see in the diagram, there is one Dask data frame and it is made up of 3 Pandas data frame. Let's look at the code here to understand this more. So I have a single node code here and I have a code in Dask. So in single node code, I'm importing Pandas and I'm reading a CSV file. Then I'm using a group by function and mean function to find what is the mean lap time for each driver. Now let's look at the Dask data frame code. So I'm importing Dask data frame here. Notice that I'm reading the CSV file the same way as I would be doing in Pandas. The syntax is same, but under the hood, things are different. So when you are reading a file in Pandas, in that case, everything is read right from the first line to the last line. But in case of Dask data frame, Dask is lazy. It is not going to read each and every line at that time. It is just going to read as much as is required. That is, it is going to read what are the columns and what are the data types, and that's it. Only when in the last line, if you see here, where I'm again finding for each driver what is the mean lap time, the rest of the syntax is same, but in the end, I have added .compute. So adding .compute means that you are explicitly telling Dask that, hey, now you need to read everything in parallel and you need to do the computation in parallel. So this is how Dask data frame works. Now with this, we come to Dask arrays. So Dask arrays can be thought of like a bunch of NumPy arrays. Again, just the way as we see here in the diagram. So let's understand this with a code here. On my right-hand side, you can see that I am creating a Dask array with NumPy array. So the NumPy array size is 4 by 4, and I'm creating a Dask arrays in chunks of 2 by 2. That means that out of this NumPy array, I would be creating a four blocks. Again, just the way as we see here in the diagram. Now, the operation in Dask array is done in blocks, meaning let's say that you have to do summation here. So the summation in this case will be done in 4 blocks at the same time first. Once the summation is done in these 4 blocks, then these 4 blocks will be further added. So more or less for this case, Dask array is 4 times faster as compared to NumPy arrays, minus the overheads, of course. Okay, so with this, we come to the last of high-level interface, which is Dask bags. So Dask bags can be thought of like bunch of list. Now, why do we need Dask bags? We already have Dask data frames, right? We need Dask bags because sometimes data is not structured. It is unstructured or it is semi-structured. For all those cases, doing the data cleaning, doing the data processing, it is much more easier in Dask bags because it's very easy to use functions like filter or map in Dask bags. Let's try to understand this again with an example. So here I have a JSON file which has some information about Formula One drivers. Now, I'm not sure if this information is up to date because it's been some time that I created this file. But anyways, back to Dask. So here I am loading this JSON file. Then I'm using filter function and I'm using map function. With this, I'm trying to find the name of drivers whose rank is less than 10. And again, as I did in Dask DataFrames, here again, Dask is lazy because so I am using .compute so that we can explicitly tell Dask to read and do the computation. And once you have done all the cleaning of data, you have done pre-processing of data, then you can convert these to flat columns. You can convert these to Dask data frames and proceed with more complex machine learning computations. Okay, so with this, we come to the end of high-level interface. Now comes Dask delay. So this is the part of low-level interface. So revising once again what low-level interface was, low-level interface will be used when you do not want to change your custom algorithm. So you do not want to introduce high-level interface inside custom algorithm. For example, suppose you started creating your single node algorithm in Pandas, for example, and you created a couple of functions. And later you realize that it is running slow. And you think that, hey, I think I need some scalability. And you don't want to change each and everything to Dask data frame. So in that case, you can keep your custom algorithm as it is, and you can just wrap it with Dask delay. Or there might be situations as well, like where your computations are complex enough that they cannot be done in Dask natively. In that case as well, you can keep your computations as it is, and just to scale it, you can use Dask delayed. So let us understand that how Dask delayed works, and it gives us scalability. Take an example of building a car. Say one way to build a car is that someone gives you instruction 1, like let's say put on a tire. You do that. Then you go back. Someone gives you instruction 2, put on a tire 2. You do that and you go back. And then someone gives you instruction 3, put on a steering wheel. So in this way, this is exactly how a single node would work. That is executing each and every function one after the another. Now, how does Dask delayed works? So the another way to build a car would be someone gives you a set of instructions. You just look at those set of instructions. You create a blueprint that how me and my 9 other friends can build this car in the most parallelized way. So then you build that blueprint, you call your 9 other friends, and then you build the car together very fast. And this is exactly how Dask delayed works. It is not going to execute each and every function one after the another. It is lazy. It is going to wait. And then explicitly, when you tell it to do the computation, it is going to do the computation in the most parallelized way. So let's try to understand this with an example. Here, I have a code which is written in single node. So here it is using pandas. I'm trying to find the maximum lap time. I'm trying to find the minimum lap time, and then I'm finding the range. And the result that you see is in C, which I'm printing here. Now, let's add some scalability to it. So we would be introducing Dask delayed. So the one way to do that is using Dask.delayed for each of the functions. Or otherwise, alternatively, you can also use a delay decorator on the functions. So now when you print your result, C, it is not going to print the result. It is going to print the object. Why? Because Dask delayed is lazy. Till now, it has not done any of the computations. But all this while, it has created a task graph. So on my right-hand side, you can see the task graph that it has created. So task delete realized that, hey, finding the maximum lap time and finding the minimum lap time, they are not related to each other. I can execute those in parallel. So this is how the task graph was built. And then in the last line, when you do .compute, when you are explicitly telling Dask to do the computation, it is going to look at this task graph and do the computation in the most parallelized way. So this was about task delay. So with this, we come to last of our low-level interface, which is task futures. So task futures is the extension of Python's concurrent future interface. It is like an alternate to delayed. But instead of being lazy, this one is immediate. So sometimes the data that you're getting, maybe you have to work on some real-time data which is streaming, so you want some immediate results. Or maybe you are working on some adaptive algorithms where your future result depends on your previous one. So for all those cases, you can use task futures. Let's see how this works. So here again, I have got the same functions which I used before, which are in single node, finding the maximum lap time, finding the minimum lap time, and finding the range. Now, the futures has this function, which is submit function. So this submit function is going to submit this task to the workers, and each of these tasks will be executed in the most parallelized way. And then the result will be stored in the remote thread, which you can extract using c.result. And it can be a personal choice as well, whether you want to use task delayed or task futures, because sometimes people don't want their computations to be lazy. They want immediate results. So in that case as well, you can use task futures. Okay, so this was all about user interfaces of Dask. Now let's come back to Formula One. Say, Lewis Hamilton has this ultimate aim of driving car fast. Now he has two ways of doing that. The first way is that he builds a car himself and then he drives fast, or he can let some constructor build a car for him and he can just concentrate on driving car fast. What do you think he did? He went with Mercedes, by the way. So just like Lewis Hamilton, even data scientists have some choices. Either they can build a Dask cluster themselves, handle all the Kubernetes, security, infrastructure issues, blah, 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 all by themselves, or they can let Saturn Cloud do all the heavy lifting and they can just concentrate on building optimized models. So let me show you that how easily you can build a Dask cluster using Saturn Cloud. So as soon as you log in into Saturn Cloud, you come to the resource page. And by the way, you can log into Saturn Cloud for free because we give you 30 hours of free computing time each month. We give you 3 hours of Dask. We give you GPU instances, and we also give you 64 GB of RAM. So I would recommend that you give it a try. Okay, so as soon as you come to the Saturn Cloud website, you will see here there are a number of resources. I've even started some resources here. So resources can be thought of like a computation environment, and each computation environment in the backend is connected to a hardware. Now, in general, whenever you are building a Dask cluster, it has to be associated with a resource. A resource can be a deployment, a job, or a Jupyter server. So let me show you that how you can build a Dask cluster using Jupyter server. So here I'm going to click it. You can make your choices here in UI itself, that how powerful you want your machine to be. Then I click on create here. Then you click on new Dask cluster here. Again, you can make choices just in UI here. You can choose that what should be your worker size, what should be the scheduler size here. You can choose how many workers you want here, and also how many threads you want. So, and that's it. You click on create. You start your Jupyter server, you start your Dask cluster, and that's it. It is ready. So I have already started this for you. So as soon as this is started, you enter a very familiar page, which is Jupyter Labs. So let me show you here again quickly the examples that we did previously. All you have to do here is that you have to associate your Saturn cluster class with Dask, and you don't need to pass any parameters because cluster is already ready for you. So we start this, cluster is ready. And here you see that I'm importing task.dataframe. This is the same example which we had done before, where we are trying to find the mean lap time for each of the drivers. So here you see I'm reading the CSV file. All the parameters are same, just the way you would be otherwise reading in pandas. And then in the end, I'm using .compute here to let Dask know that this is the time. You have to load your data in parallel and do the computation. And there you go, you have the results. Okay, let's also see that how task delayed works. So here I have a custom algorithm, which is in single node. I'm using pandas here. Let me execute this. So when you execute this, the single node one, the C is the variable which is having the range lap time, and I'm printing it. Now, let's add some scalability to it. So I'm getting my clusters ready. Now, here I'm wrapping this with task.delete. And now when I'm going to print C, it is going to print an object. So let us see that all this while the task graph was getting created, how does this look? So for that, we can use c.visualize. So when you do c.visualize here, you can see the task graph. And now the computation will be done just the way you see in the task graph. And there you go, you get the results here. Okay, so back to my slides here. Now with this, I want to talk to you next about Dask dashboards. This is the video of Dask dashboards, how it works. So let me just pause it and talk about it. Dask dashboards has some graphs in it. Whenever you are trying to make some decisions on how you should be configuring your Dask clusters, whether you are using enough workers, whether you need more, or how your tasks are processing, you can just look at your Dask dashboard and make those decisions. So let me just start this again and walk you through it. So the task stream here that you see, each of the rectangle here represents a task. And also in the progress bar, you can see that each of the bar represents a task. And the color coding is similar. So each color represents a task in task stream, and the same thing is carried in the progress bar itself. Now, on my left-hand side, you can see task processing. So this is showing that how many tasks at that point is being done, carried out in each of these workers. And the same way, bytes stored is telling you that how much memory is being consumed by all the workers in total here. And here you can see that how much memory is consumed by each of the workers as well. Okay. And also I will be showing you Dask dashboard live when we will be seeing some demo examples in future. Okay, so this was all about the basics of Dask concepts. Now let us see that how powerful Dask is. So with this, I come to hyperparameter tuning. Hyperparameter tuning in general can take a lot of time. It can take hours as well. But in Dask, it can really scale up your computations. So let's look at the example here. First, I'm using a single node, and then I'm here using Dask. So for doing hyperparameter tuning, I am using Grid Search CV. Now Dask has this package, which is very much whose API is very, very similar to scikit-learn. So the syntax remains almost same. So if you're going to see both of my codes, there is hardly any difference in that. But there is a lot of difference if you are going to see the results here. So on my right-hand side, if you look at the results, you will see that for hyperparameter tuning took 3 hours in my single node code. Then when I used 3 workers, it took the training came down to almost 1 hour. And then I used 10 workers and it came down to 20 minutes. And then I used 20 workers and execution just took 11 minutes. So you can decide that how powerful you want your hardware to be, and your training will be done very fast. So with this, and also I will be showing you this example in the demo. So now we know that Dask is fast, but can it be faster? Yes, it can be faster if you can integrate Rapids along with Dask. So what are Rapids? Now, Rapids is a suite of open source libraries. It is used by scientists for using GPUs in their machine learning pipelines. So let's take an example. Say when you are running your computations using pandas, they are run on CPU. Now, Rapids has these special packages whose API literally mirrors the API of these popular packages of single node. For example, Rapids has this library which is known as CUDF. So CUDF's API literally mirrors the API of pandas, meaning the syntax remains almost same, but CUDF does its computations on GPU. That means you are scaling up. So now when you are going to combine Rapids and Dask, you are not only scaling up, you are scaling out. Say, for example, you are using Dask DataFrame. So Dask DataFrame natively is made up of a bunch of pandas DataFrame. But when you are integrating Rapids and Dask DataFrame is made up of a bunch of CUDF data frames. That means that all the computation is happening in parallel and it is happening on GPUs. And again, I will be showing you shortly this example in the demo. Also, you can integrate Dask with PyTorch, and you can run a single model across multiple workers. Or if you want, you can run multiple model on multiple workers as well, because there is this library, Dask PyTorch DDP, which makes this possible. Now, let me show you all these examples live. So first, let us look at hyperparameter tuning. First, I'm getting my clusters ready. There you go, it is ready. Also here you get the link of Dask dashboards. You can see that how many workers you have and some other information. Now I'm going to read the file. So this data is New York taxi data. It is a public data and I have stored it in AWS S3. So the parameters that you see here that I'm using here, they are literally the same parameters you would otherwise be using in pandas. No difference here. But in the second line that you see where I'm using .persist on my data frame, so this means that I am letting Dask know that, hey, you are lazy and I have some complex computation to do moving forward. So please materialize these Dask data frames and keep them in memory until I ask you to do so. So that is the meaning of .persist here. Now, the next section of code, this is all feature engineering and feature extraction. No change here. And now I would be doing my grid search CV. So here I've created a pipeline and notice that I have used scikit-learn.pipeline here. So as I told you before that Dask integrates very nicely with the existing Python ecosystem. So I can use scikit-learn pipeline here. And inside that, for one hot coding, I am using Dask ML dummy encoder. So yes, Dask can integrate very nicely with scikit-learn. Then I'm doing grid search CV and passing my parameters and pipeline. So let me run this. In the next cell, you will see that I have wait for workers. So I have 20 workers, and this is just a way of telling kernels to wait till all my workers are online. And this can, there is an alternate as well to this. You can check that in Saturn Cloud UI as well. So let me run this real quick. And then we come to the actual fitting. So while this is running, I can even show you the Dask dashboard here. So you can click here on Saturn Cloud UI and look at the Dask dashboard. There you go. You can see that how your training is taking place, how many tasks are getting processed in each workers, and your training is almost done. So each color, as I said, represents a particular task. And the training is almost done. Let's go back. So hyperparameter tuning, which can sometimes take minutes or even hours, just got over in 30 seconds. So with this, let me show you the next example, which is about how you can integrate Rapids and Dask. So again, I am going to import some necessary libraries here, which we will be talking about later. And then I'm going to spin my clusters here. Again, I'm using wait for workers just to ensure that all my workers are online. Now let's look at this code again here. So here I'm using task_cudf, which we imported here. So this is the special library where Dask data frame will be composed of a bunch of CUDF data frames. That means that the training will be done in parallel on a bunch of GPUs. So, and again, the parameters that I'm using here, they are literally the same, which I would be using in pandas as well. But this dot persist here is again from Dask, which means that we want to materialize, we want Dask to know that we want to materialize a data frame and keep that in memory so that we can proceed with some complex computations. So let me just run this real quick. And then in the next cell, let us see that how many partitions are there. So we have got 3 partitions here. Now the next set of code again is very similar. There is no difference. You would be otherwise doing your feature extraction or feature cleaning here. So let me run this. We are prepping the data. We are just running the function above. Now we would be running random forest classifier. So this random forest classifier is again part of cuml.dask.ensemble. So this is the integration of Rapids and Dask. Let me run this. And then let's do our training here. And it's done. So you have run your random forest classifier training in a couple of milliseconds. So with this, we come to the last of our example, which is training our PyTorch model across multiple workers. So here again, I would be loading some necessary libraries. And okay, so the data here I'm using has got lots of pet names. So we would be fetching this data to a neural network. The training will be done, and as an output, we will be getting some realistic looking funny pet names. So today I won't be deep diving into how deep learning is done here. Rather, we would be concentrating on how we are integrating Dask with PyTorch. So first, we are loading our data and we are converting it into vectors so that it can be fetched for training purposes. Let me run this. And the model that we have used here is LSTM. Now I'm going to import some necessary libraries. Notice that I have used Dask_PyTorch_DB. So this is the special package which will do all the magic moving forward. So now let me just quickly start the training and then I can walk you through it. Okay, let's get back to this function training. So here again in training, most of the things are same you would be otherwise doing in PyTorch. There are 1 or 2 differences which I would like to point out. Firstly, we are using here distributed sampler. So distributed sampler is a function of PyTorch which enables the distribution of data across multiple workers. Now, once the data is distributed, we would also want the workers to establish communication amongst each other. So once you have defined this model, after that, I am wrapping this up with DDP. So DDP again is a function of PyTorch, and it established the communication among the workers. Why do you need that? We need that because whenever multiple workers are training a single model, they need to be in sync so that they can update the gradients together. A set of data will be passed to each of these workers. These workers will be doing the training on them and then syncing the gradients so that the weights can be tweaked. Okay, so now I have spent my clusters again. They are ready. And in this next, okay, so my training is also done. So this is exactly where, if you see dispatch.run, this is one of the functions of my package, which was here, Dask, PyTorch DDP, and this is doing all the magic. So this is passing my training function, the training function which I had created here to all the workers. So that is how you are able to distribute your training, your single model, and get it trained amongst all the workers. And then your result, your training model will be stored on this path. So my training is done. I can close my clusters now. And this is the function which can generate some funny looking pet names. I can load my model, and then I can generate 5 pet names. And there you go. I have 5 funny looking pet names. And imagine I trained a neural network in a couple of seconds, and that's it. This is the power of Dask. So with this, I will just wrap it up all for you, that what all we learned today. So we learned that Dask increases the speed of your computation. The interface is very familiar. So if you know how to write your functions in Python, so switching to Dask won't be a big deal for you. If you have a custom algorithm which you don't want to change, you can just wrap it up with something like Dask delete. And lastly, Dask integrates very nicely with existing Python ecosystem. So this is all from my side, and I would encourage you, if you want to try all these examples, you can log into these links. If you want to try the Dask example, you can go to scld.io-x-py-dask. If you want to try the Dask and Rapids function, go to this link, scld.io-x and PyRapids. Or you can try Dask and PyTorch as well. So these are the 3 links where you can just click on and look at these examples. And lastly, we also have one very interesting webinar coming, which is on February 10th. It will be by Nathan Ballou and on a very interesting topic, what to do when your data gets big. So you can register for free on the link given below, scld.io Big Data Webinar.